Newton's laws are the basics of the most fundamental part of this course. So you have to really try to understand Newton's laws to understand how external forces are applied to a body and then transferred to the ground, and how the ground has a reaction force that keeps a system in equilibrium. The book that we have mentioned also has both SI units and English units. And in the University of Michigan also, pounds, slugs, and feet and inches are also covered. So although it's a somewhat of an older system, I still cover both so that those of you who also go over to University of Michigan for the dual degree program won't be lost when it comes to the imperial or English units. It's good to study a bit of the conversions and see how you might go through that to convert from pounds to newtons, slugs to kilograms, feet to meters. For example, I weigh 180 pounds. So in 1 pound, there's 448 newtons, right? So this would give me my weight in newtons. And so if I wanted to then give mass, I could convert it. But here, this would give me my weight in newtons. So this would be approximately, well, exactly 800.64 newtons. Now, if you see, if I had put a decimal place here, that I had 3 significant figures, which means I would be looking for 3 significant figures in my answer for this over here. If I had more, it's somehow I did a calculation that gave me more accuracy than the number I gave in the beginning. So I typically wouldn't want to give something where I had 1, 2, 3, 4, 5 significant figures when I had only listed 3 in the beginning. So what I'd like to do is I'd give an answer that's 801, and that's how I would go through listing that. Now, if I wanted to then give my mass instead of weight, then just a simple formula for the weight is equal to the mass times gravity. So if I wanted mass, I'd just weight by gravity, and then I'd have that. So here's my weight, and then I'm going to divide by gravity. So that would be 9.81 meters per second squared, right? So then I have the newtons here. Everybody know the basic the unit of newtons. So newtons would be 1 kg meter per second squared. So if I didn't show it this way, and instead I just said kg meter per second squared, you can see that the units here and here will cancel out, and I'll be left with kg in the answer, or kg in the answer. And that's what we want. So we would then have 81.7 kg. So that's helpful. But what if I wanted to then convert back to mass in slugs? It's not typically used in the United States. We don't really use slugs, but that's what it is. And if you wanted to, you could. So let's go ahead and do that. So this is 81.7 kg. And in 1 slug, there would be 14.59 kg, which would be 5.60 slugs. Okay, so this is nice. I mean, I have a nice round answer. There is one issue to this, and some of you may a bit of a question, which is if I wanted to convert directly from pounds to slugs, which would have been the more straightforward way of going, I would have said 180 pounds. And in one slug, I have sorry, that was a mistake. Let's see. There we go. 32.2 pounds. So if I gave this answer, it would be 5.59 slugs, which is approximately the same, and there's some rounding differences that would have given me that difference, right? So you can see here in some rounding errors through the calculations, you're going to end up with a 0.01 error in the slugs. But anyway, it's helpful to go through the conversions of different units and to know the basic units that all of these are made up of. When we get to the mechanical problems, when you're trying to convert different pressures or stresses, that becomes something that you want to know the basic units. You want to know how to convert from pressures, moments, and different units, so that you can specify problems in engineering to technicians that you might work with. And that's extremely helpful. No matter where you are in the world, you're going to have to sometimes do conversions. And then we can translate our analysis and our work to others that can help us. Sometimes I give an exam or a quiz, and the answers will typically be way too many significant figures. Many calculator will put out. So 16 digits or something like that, just to be very, very accurate. It's not your calculator that determines the accuracy. So make sure that you understand that, and that every time you're giving a problem, that you look at the significant figures before you give the answer. Okay, so I've already given some of the syllabus already. We've already gone through that. So make sure that you have the 4th edition. If any of you have troubles with that, please send me an email. And just some of the content from that. So while the first chapter deals with units and conversions, which many of you can go through quite quickly and easily, the second chapter goes through force vectors, which are the first part of really getting more into calculating forces, their magnitudes, their directions, such that we can calculate internal and external forces on a body, and then later in mechanics, calculate their deformations, how they deform or bend or stretch or compress so as you go into your book to study, it's important that you have a good foundation of vectors and how to set that up. In the beginning, it's just a lot of geometry, and also how we specify what is a vector, right? How do we show it? How do we write it? The language of doing that. So typically, when we talk about, we have a vector. If you can see here, and I think I have a spotlight here. Spotlight. Okay, so you can see the vector here. So we typically have a capital with or lowercase, and then you'll have a little arrow on top of the letter. And so that helps you to know that this is a vector, right? Which means it specifies direction and magnitude. But if you just wanted to know the magnitude, then you can take the norm of the vector. And so so you can take the magnitude of the vector A. Now, many of you have probably already done this in physics. But you know that there's a difference between something like mass and volume and length and maybe temperature, right? These are directionless directionless quantities, right? Such that you don't have a direction of these. But what once we go through the vectors, you'll be able to even work on problems like cable stayed bridges. You can see that this is a screenshot of the top of the columns of a cable stayed bridge, and you can see this reinforced concrete column going through the center, and then steel cables coming out of the column. So that column is in tremendous compression, being pulled down by those steel cables. Now there's a force in tension inside those steel cables that's keeping this whole system in equilibrium, and those cables support the bridge deck of a bridge. And this is how this beautiful bridges work. There's a force inside each cable which is along the direction of the cable. So if you know more about the geometry of a bridge or a cable, you can say something about the forces that are inside the cables. And that's where a lot of this, the ideas of the how to solve some problems for equilibrium come through, is that we first need to know a bit of the geometry, and then we need to know how to calculate the forces that are inside of an object, and then we can try to better design it and have design new structures and make sure that they are going to be robust. So I assume everyone is already somewhat familiar with scalar multiplication and division, but you can take a vector and you can multiply by a scalar and you're going to change its length, or you can multiply by a negative, for example, you're going to change its direction. And so some of these are shown here. So you can make sure you know your scalar multiplication to division. Some of the first rules that we go through when we're going into the second chapter of the book, and the triangle rules and parallelogram rules. These are simple visualizations of how to add vectors together to get a resultant vector. And so you can see here, R is the resultant. R is the resultant vector of the summation of A and B, and so the vectors are placed start to start, and then they're duplicated such that A is added at the end of B and B is added at the end of A, and where they intersect is the point P, so that you still have the start to the end would be your resultant vector. So this is the parallelogram rule. Typically, we don't use these rules so regularly. They're good visualization, and as you use more equations and go through that later on to make your work faster, but you still visualize all of the vectors and how they're added and that kind of stuff to have a good feeling and confidence in your solutions by doing the parallelogram rule in your head. Maybe it sounds a little silly, but I still do the parallelogram rule in my head. And so it's good to go through it in the beginning to get your confidence up to make you know your answer. So although you can do the calculations, if you made a mistake, you can still know it if you're doing this visualization in your head. So it's good to visualize what you're doing. So the parallelogram rule and the triangle rule, they both work quite well to be able to visualize the addition or subtraction of vectors. As I had said before, the forces in a cable are along the length of the cable. So if you can see the hook that's holding these two chains, the chains that are here labeled with the force internally F1 and F2. And then what you would like to know is, what is the resultant force? Well, the resultant force is going to be this F sub r, resultant force, that's pointing downward. Well, if you think about it, there must be another force that's holding that in equilibrium, and that's the vertical cable on the upper side. So if you see here, there must be another force in this direction. So that would mean that there's a force where this sort of purple arrow is here. And so this force would be acting here on the opposite direction of FR to be able to hold this whole system up, right? And so so this is a visual to help you to understand that the forces are in these cables, and then there's a resultant force that is coming from the summation of these two. So whatever that object is, whatever object is being held by the hook is then taken by the forces F1 and F2.